Ryan Firebee is the most adaptable jet-powered target drone system in use for training by the United States Army, Navy, and Air Force today. The past several years, which have seen the development of today's missile inventory, have witnessed the parallel evolution of the Firebee target system, which has anticipated the requirements of more sophisticated and efficient weapons. The military need to service the newer weapons systems with a higher performance, more versatile target introduced this newer, improved version of the Firebee family, the Q2C. On-station endurance is a major factor of efficient target performance, since this determines the number of presentations or missile firings that may be accomplished on each flight. The Q2C has accomplished a maximum altitude of 59,800 feet and a maximum endurance of 97 minutes, of which 77 minutes were above 50,000 feet. Maximum speed attained has been Mach 0.96 at 51,000 feet. Specification performance requirements are consistently being exceeded in all categories. Radar augmentation in the XCL and S frequency bands is provided by traveling wave tube amplifiers. Using this augmentation, the radar reflectivity of the Q2C can be increased to simulate a bomber-sized threat to air defense radar operators. Provisions have been included for the installation of radar tracking beacons, which give positive target identification. The Q2C is recovered by parachute. The cycle is initiated in various ways, dependent on target altitude and circumstances. Included is a power-off glide phase, which is initiated after fuel depletion. The target will remain in glide until recovery is commanded. It will also recover automatically if battery voltage drops below a preset level. Glide phase permits the Firebee to be returned to a predetermined area favorable to retrieval. After the target touches down on land or water, the parachute is automatically released to prevent damage by dragging. Retrieval is accomplished by helicopter, boat, or truck, and the Q2C is returned to base for repair and reuse. B-26s, P-2Vs, or GC-130 air launches, or zero-length ground launches fulfill launch requirements for all missions, ranging from low-level evaluation to high-altitude operations in which multiple presentations per mission demand maximum time on station. Because of a basic Ryan philosophy, that the original concept of any system must contain growth potential, as increasingly efficient aerial weapons demand a high-performance target, there will always be a Firebee ready for any mission assigned. Because the kill probability is likely to be quite high in Army surface-to-air guided missile training and service practice, another approach to using the Firebee and a less costly auxiliary target in such missions is now being developed. To provide a realistic target and at the same time reduce costs to a minimum, Ryan has developed the Firebee towbee system, consisting of a Firebee towing an inexpensive target called towbee. For guided missile training, the towbee will be the target tracked and killed during the firing exercise. With the use of passive radar reflecting devices, the towbee will appear like a large enemy bomber on the missile radar tracking screen. To better understand the Firebee towbee system, let's follow a typical missile support mission. After the JATO bottle is attached and aligned to ensure proper launch trajectory, the Firebee is moved to the launch pad. The target is taken from its handling aid and positioned on the rail launcher. The towbee bridle, a V-shaped steel cable, is attached to the sides of the bird through explosive release fittings. These fittings can be actuated during flight to release the bridle and towbee. To prevent entanglement of the tow bridle with the launcher rails, the bridle is hung on a simple A-frame mounted on the end of the launcher. Approximately 1,800 feet forward and to the left of the Firebee launcher is the towbee launch support rack. After the 16-pound towbee is placed in the launch rack, a nylon tow line attached to the nose of the towbee is uncoiled and laid on the ground back to the Firebee launch point. There it is attached to the V-shaped bridle. Now we are ready for the launch countdown. From the launch control bunker, external electrical power is applied to the target. Next, the engine is started, and a series of direct checkouts of the target are made through the umbilical cord. At the target control center, a series of remote checks are also made to assure proper radio control operation. The final countdown begins. During the JATO boost, the towbee tow line forms a graceful arc between the ground and the Firebee. The towbee is pulled vertically from the launch rack, then arcs over and trails the Firebee. From the target control center, the Firebee towbee combination is flown to the desired missile firing area. The missile is fired, followed by a hit on the towbee and its destruction. The towbee bridle is released. Then recovery is commanded, and the Firebee settles to the ground for retrieval and reuse on subsequent missile support missions. The Ryan Flexwing flying test bed is the first of an entirely new class of flight vehicles using wings with rigid metal-covered surfaces. The flexible wing is a plastic-coated nylon material attached to a keel and leading edge members so as to form an arrow or V-shaped kite-like surface which supports the platform suspended beneath the wing. The manned test bed permits engineers to make more detailed analyses and evaluation of the flexible wing concept than has been possible with wind tunnel and model testing. Such research has already been done by NASA, which developed the concept based on original work by Francis Gallo. The remarkably wide range of applications of the flexible wing includes both manned and unmanned vehicles, which may be either powered or unpowered. In size, they may vary from small, powered reconnaissance drones maneuvered by remote control to huge, unpowered wings capable of recovering payloads and rocket boosters of 50 tons or more. The flexible wing concept offers an extremely lightweight, large aerodynamic lift surface and a simplified control system using center of gravity shift instead of displacement of conventional control surfaces. Designed to be folded into a package, the flexible wing can be quickly deployed, faster than a parachute, for any of the varied missions to which it is applicable. Span of the Flexwing test vehicle is 39.4 feet, and the wing area is 555 square feet when fully deployed. The Flexwing is inherently stable about all three axes because of the self-righting moment, or pendulum effect, created by the position of the suspended mass well below the lifting area. After Ryan conducted 10 hours of testing to demonstrate safety factors and functional characteristics, further flying and applications engineering is being done under a contract with the Army's Transportation Research Command. Ryan also holds a contract with NASA to study adaptability of the flexible wing for recovery of the first stage booster of the Saturn space vehicle. Contracts are also being negotiated by Ryan for other military applications of the Flexwing. Helicopters towing the flexible wing as a glider will be able also to transport many times as much weight in troops, cargo, or fuel as the helicopter alone can carry. The helicopter-towed wing can transport large amounts of cargo, not only between bases, but also from aircraft carrier to shore. Small, inexpensive surveillance drones launched by 2 troops in the field are possible with the Flexwing concept. A drone on a typical surveillance mission would be fired out and propelled by a small pusher engine to enemy territory. After gathering data over the target, it is flown back to the launch point. Prime advantage would be the ease of maintenance and low relative expense of a drone system which might also serve an alternate mission as a decoy. Extremely large payloads can be dropped from cargo aircraft at low altitude and high speed. Also, offset delivery and spot landings can be made. Weapons delivery from combat ships of the fleet while at sea is possible using a remote-controlled, powered Flexwing to carry the warhead to its target. Today's radar-guided aircraft are making Atlantic flights on a routine basis with greatly accelerated speeds at considerably higher altitudes. These conditions, coupled with increasingly crowded airspace, make aircraft all-weather navigational control requirements a more exacting necessity. Providing this precision in all types of aircraft and helicopters, Ryan-designed sub-miniature Doppler processing circuits have been developed into these small, lightweight representative units. Ryan is the world's largest producer of continuous wave Doppler navigation systems, and the only company that has Doppler navigators in production for helicopters today. Certain characteristics are common to all Ryan airborne navigation equipment. The most important of these is the utilization of pure continuous wave Doppler techniques. Pure CW is the most efficient and versatile approach to Doppler navigation. It does not exhibit altitude holds, insensitivity at high altitudes, or inadequate performance over smooth seas and deserts. Also, CW permits operation at 0 altitude. The continuous wave energy generated by this navigation equipment is concentrated into narrow beams of radiation directed toward the ground. Energy is transmitted along each beam at frequency FT. The terrain reflects a portion of the energy back into the antenna at frequency FR. With beams directed aft, the frequency of the reflected energy is lower than the frequency of the transmitted energy because of the component of aircraft velocity relative to the ground in the direction of the beam axis. Due to the finite beam width, the frequency difference between FT and FR actually is a spectrum. It lies in the audio frequency band, and the center frequency of the spectrum is proportional to the aircraft's ground speed. The higher the aircraft speed, the greater the frequency difference. This frequency shift phenomenon is known as the Doppler effect. It is the basic principle used in Ryan Doppler equipment to measure the speed of an aircraft. With one beam, only one component of the aircraft's speed can be measured. But with 2 or more beams, it is possible to measure the aircraft's heading speed, drift speed, ground speed, and drift angle. Portions of this data are available for display to the pilot and for further processing in additional data displays. Exemplifying this is a plotting board with a predetermined course overlay. A pilot may fly any course and visually follow his aircraft's position and ground track. This combination can be used to facilitate search patterns and station keeping. In addition to these applications, continuous wave Doppler radar can supply the inputs to other plotting boards with map overlays to give a pictorial identification of the aircraft's present position relative to a base or destination. This all-weather and all-terrain capability is of prime importance in conditions where line of flight must be maintained within close tolerances. In these helicopter applications, Ryan Doppler systems can automatically detect motion or induce or prohibit motion over the ground or water. This capability is particularly essential to the helicopter, which must make repeated manual or automatic transitions. For all types of fixed-wing aircraft, these versatile Doppler systems automatically and continuously compute and display ground velocity and other navigational data over sea and land, without the aid of ground stations, wind estimates, or true airspeed information. The inclusion of a navigational computer provides outputs for tie-in with position, course, and distance computing equipment, inertial navigation equipment, and terrain clearance radar. The Doppler's high sensitivity permits operation over a wide range of aircraft drift, pitch, and roll angles with no attitude holds. Ryan's self-contained Doppler equipments provide all-weather navigation, high performance over smooth seas, all-terrain zero-altitude operation, stabilized hovering control, and they meet the altitude and speed requirements of modern aircraft and drones. The Ryan Firebee is the most adaptable jet-powered target drone system in use for training by the United States Army, Navy, and Air Force today. The past several years, which have seen the development of today's missile inventory, have witnessed the parallel evolution of the Firebee target system, which has anticipated the requirements of more sophisticated and efficient weapons. The military need to service the newer weapons systems with a higher performance, more versatile target introduced this newer, improved version of the Firebee family, the Q2C. On-station endurance is a major factor of efficient target performance, since this determines the number of presentations or missile firings that may be accomplished on each flight. The Q2C has accomplished a maximum altitude of 59,800 feet and a maximum endurance of 97 minutes, of which 77 minutes were above 50,000 feet. Maximum speed attained has been Mach 0.96 at 51,000 feet. Specification performance requirements are consistently being exceeded in all categories. Radar augmentation in the XCL and S frequency